Welcome to the deep dive. We take complex stuff and, well, try to make it make sense.
That's the goal.
And today, we're tackling something that's really fundamental, but maybe a bit mysterious. The inverter.
Ah, yes, the inverter. Quietly working away behind the scenes.
Exactly. We had listeners ask us to break this down, for beginners, cut through the jargon.
Good plan. They're everywhere, but not always obvious.
So our mission today, what are they really? How do they actually work? And why are they so important?
Especially now with renewables and all that.
Right. And we're drawing insights from Gale, that's John Bioncio's book, published by Gilbert, roughly Beginner's First Steps in Electricity.
A solid starting point.
Okay, let's unpack this. So to really get a grip on inverters, maybe we should quickly rewind to the basics of electricity itself.
Good idea. It all starts there.
We've got two main types we deal with, right? Direct current DC
Yeah.
and alternating current AC.
AC is generally what comes out of your wall socket. Powers your fridge, your lights, that kind of thing.
And DC, that's more like batteries.
Batteries, exactly. Your phone battery, car battery, and importantly, solar panels. They generate DC. And here's the interesting part. They're different, DC and AC, in how they flow and are generated.
Okay.
But the clever bit is we can change one into the other. We have devices for that.
Right.
So take solar power or energy stored in a big battery, both DC.
Right.
But then you want to say plug in a hairdryer or your laptop charger. Those usually run on AC.
Ah, okay. So you can't just plug a hairdryer into a solar panel.
No, definitely not directly. There's a mismatch. How do you bridge that gap? That's the core problem.
And that's where the conversion device comes in.
Precisely. It's absolutely central to making things work together.
So, like, my car battery is putting out, 12 volts DC?
Typically.
But if I want to run something small, like a light, or charge my phone, which needs, say, 220 volts AC,
Yeah.
That's the inverter's job.
That is exactly the inverter's job. It's the key. It takes that DC, could be 12V from your car, could be higher voltage DC from solar panels, and it transforms it into the AC that our standard appliances use, usually 220V or 120V, depending where you are.
That makes things so much more flexible.
It's vital. Think about camping using an inverter to power things from your car battery.
Yeah, I've seen those.
Or, much bigger scale, connecting huge solar farms to the grid. The grid is AC, the panels make DC, you need inverters in between.
So without them, no large-scale solar power feeding into our homes.
Pretty much. It's the crucial link. The key thing for beginners is just knowing that electricity isn't always usable straight away, but inverters make it adaptable.
Okay, that makes a lot of sense. It's like an electrical translator.
That's a good way to put it, yeah.
But let's dive a bit deeper. Is it just converting DC to AC, or is there more going on? What's the, precise function?
Right, it's not just a simple swap. An inverter is, yes, primarily a power conversion device, DC in, AC out.
Okay.
But, and this is crucial, it also shapes other things about the power.
Shapes them. How so?
Well, it can change the voltage level. And it sets the frequency.
Ah, the frequency, like 60 hertz.
Exactly, like 60 hertz or 50 hertz in other regions. And the voltage, getting it up to that 220V or 120V standard. So think about it. DC from a battery is steady, maybe low voltage. The inverter takes that, makes it alternate back and forth 60 times a second, and boosts the voltage to the right level.
And it has to be a specific shape of AC too, right? You mentioned waveforms.
Yes, exactly. That's about the quality. It tries to create a smooth sine wave, which is what the grid supplies and what most electronics expect.
Not just any alternating current.
No. Cheaper inverters might make a blocky modified sine wave. It works for simple stuff, but sensitive electronics. They might not like it. Buzzing, overheating, could even damage them.
Wow. So the inverter is really controlling the quality of the power too.
Absolutely. It's shaping it precisely. Especially vital when you're connecting DC sources like solar or batteries to our standard AC grid. It has to match perfectly, be safe, be usable.
That shaping idea, it makes it sound much more sophisticated than just flipping polarity. It's refining it.
It is. It's quite an active process.
I like that. Okay, to really see this in action, could you walk us through an example? Like the solar power journey you mentioned.
Yeah.
That seems like a perfect case study.
Definitely. Let's trace the electricity from sunlight hitting a panel to powering your toaster. It shows the inverter's role perfectly. So first up, step 1, raw DC production. Sunlight hits the solar cells, photons, not electrons loose, basically, and that creates direct current DC electricity.
Raw power.
Raw power, exactly.
Yeah.
But it's Well, it can be a bit bumpy. The voltage might fluctuate with clouds, sun intensity, temperature. It's not quite ready for prime time yet.
Right, it's unstable.
A little bit, yeah. So that brings us to step 2, DC refinement. This raw DC, it needs conditioning. It usually goes through what's called a power conditioning unit. Sometimes this includes the battery, sometimes it's separate.
Conditioning, like cleaning it up.
Exactly like cleaning it up. Think of a water filter. This unit stabilizes the voltage, smooths things out. It often does smart stuff too, like MPPT, maximum power point tracking, to squeeze the most possible power from the panels at any moment.
Maximizing efficiency.
Right. So now you have a nice, stable, good quality DC supply. That's key. Raw DC often isn't directly usable, needs that cleanup.
Got it. Stable DC is ready.
Now for the main event. Step 3, AC conversion. This cleaned up DC flows into our hero device, the inverter.
Here it comes.
And this is where the magic happens. It takes that smooth DC and starts that transformation process, converting it to AC, shaping that sine wave, setting the frequency to 60 hertz, adjusting the voltage to 220V, all that stuff we talked about.
Doing the translation and the quality control.
Precisely. Which leads us to step 4, usable AC output. The inverter sends out that nice, clean 220V AC power.
Ready to use?
Ready to use in your house for lights, appliances, everything. Or ready to be safely exported to the main power grid.
And you mentioned inverter quality being important here.
Critically important. A cheap, poor quality inverter, maybe making that rough, modified sine wave. It can cause problems for your sensitive electronics. TVs, computers, even some motors might run hotter or less efficiently or wear out faster.
So the inverter's performance directly impacts the health of your appliances.
It really does. It determines the quality of the electricity powering your home, especially in an off-grid or solar setup.
That water purifier analogy really sticks. You need clean water before you bottle it, clean DC before you convert it.
Okay.
So we know what it does, where it fits. But the engineer in me always wants to know how. What's the core principle? How does it actually make steady DC alternate?
Right. Okay. Let's pull back the curtain a bit. The fundamental principle at its heart involves sets of electronic switches, very fast switches.
Switches.
Often arranged in a configuration called an H-bridge. Imagine the letter H. You have switches on the vertical legs.
Like 4 switches.
Typically 4, yeah, grouped in pairs. And the load your appliance or connection to the grid is on the horizontal bar of the H.
Okay, I can picture that.
Now, the inverter's control circuit orchestrates these switches. It closes one diagonal pair, letting current flow one way across the horizontal bar.
Left to right, maybe?
Left to right, sure. Then, almost instantly, it opens that pair and closes the other diagonal pair. Now current flows the other way.
Right to left.
Exactly. And it does the switching back and forth very rapidly.
How rapidly?
Well, to get 60 hertz AC, it needs to complete a full back and forth cycle 60 times every second.
Wow, okay. That constant flipping is the alternating current.
That's the core of it, yes.
Yeah.
Now, just switching fully on and off like that creates a very square, blocky wave, not that smooth sine wave we want.
Right, the modified wave you mentioned.
Yeah. So for better quality, pure sine wave inverters use a technique called PWM pulse width modulation.
PWM. Sounds fancy.
It's clever. Instead of just on-off, they switch on and off extremely fast, many times within each cycle, varying the width of the on pulses, short pulses, longer pulses. By varying these pulse widths in a specific pattern, they can effectively carve out a shape that very closely approximates a smooth sine wave. It's like rapidly flicking a light switch to make the light seem dimmer or brighter, but for electricity.
Ah, I see. Sculpting the wave with tiny pulses.
That's a great way to put it. And the voltage change from, say, 12V DC to 220V AC.
Yeah, how does that happen?
That usually involves a transformer. It can be integrated into the process. The rapidly switching AC, even if it's low voltage initially, is fed into a transformer which steps the voltage up.
Just like transformers on power poles, but smaller.
Same principle, yeah. That's how your little car inverter turns 12V DC into 220V AC. Now, real inverters are obviously way more complex than this simple picture. Lots of extra circuits for filtering, protection, efficiency.
Smoothing things out, making it robust.
Exactly. But that H-bridge switching principle, often with PWM, that's the fundamental engine inside. Pretty neat when you think about it.
It really is neat. Such a core, clever idea powering so much. Which leads to another question. Why now? Why are inverters seemingly everywhere these days? Were they always this common, or is this relatively new?
That's a great question, and it points to a huge shift in electronics. Historically, No, they weren't common like this at all.
Really?
Yeah, before we had advanced power control semiconductor devices making a good quality inverter that could handle decent power, it was really difficult. Bulky, inefficient, expensive.
Hmm.
Trying to do that rapid, precise switching with older tech, like mechanical relays or early transistors, almost impossible for high-quality AC.
So impractical for most uses.
Pretty much. What really changed the game, what's truly revolutionary, is the development and especially the falling cost of modern power semiconductors.
Like what specifically?
Things like MOSFETs and IGBTs. These are tiny electronic switches, but they can handle a lot of power, and they can switch on and off incredibly fast, millions, even billions of times per second, with pinpoint accuracy. And they've become much cheaper and much better over the last few decades. That technological leap is directly responsible for the affordable, reliable, efficient inverters we have today.
So it's really the semiconductor revolution enabling the inverter revolution.
Absolutely. It unlocked the potential of that H-bridge concept and made it practical for everything from tiny phone chargers to huge grid-scale systems.
That makes sense. Semiconductors changing everything again. Where else, beyond the obvious solar and maybe car examples, have these better, cheaper inverters made a big difference?
Oh, their impact is huge, often in ways people don't even realize. Take industrial motors, for example.
Okay.
In factories, pumps, fans, big air conditioning systems, they often use variable frequency drives, or VFDs. A VFD is essentially a sophisticated inverter.
And what does it do?
It takes the standard AC power from the grid, often converts it to DC internally, and then uses an inverter stage to create AC again, but at a precisely controlled frequency.
Why control the frequency?
Because the speed of most AC motors is directly related to the frequency of the power feeding them. So by changing the frequency, the VFD can precisely control the motor's speed.
Instead of just on or off.
Exactly. Instead of running a fan full blast all the time, you can slow it down when you don't need as much airflow. The energy savings can be enormous. It's a massive efficiency gain in industry and buildings.
Right. Huge energy savings. Makes
Mhm.
sense. What else?
Well, electric vehicles, EVs, are full of inverters.
Really? Where?
The main one takes the DC power from the big battery pack and converts it into AC to power the electric motors that actually turn the wheels.
Okay, driving the car.
Yep. And also for regenerative braking, when you slow down, the motor acts like a generator, producing AC, which then often goes through another conversion process involving inverters to charge the battery back up. DC back to DC, but AC is involved. Even the onboard charger that takes AC from your house to charge the DC battery uses inverter principles.
So they're critical components in EVs.
Absolutely critical. And then there's UPS systems, uninterruptible power supplies.
For computers.
Yeah, for computers, servers, data centers. When the grid power fails, the UPS instantly kicks in. It uses its internal battery, DC, and an inverter to generate clean, stable AC to keep the connected equipment running without interruption.
Lifesavers for critical systems.
Definitely. And even in everyday appliances now. High-efficiency air conditioners, refrigerators, washing machines. Many use inverter technology to control the speed of their motors or compressors precisely. Leads to quieter operation, better temperature control, and again, significant energy savings compared to older on-off designs.
Wow. So they're really embedded everywhere, optimizing and enabling.
They really are, making things more efficient, more controllable, and enabling the use of different power sources together.
What a journey today, seriously. From just the basic idea of AC and DC
The two fundamental types.
to seeing how inverters act as that crucial bridge, that translator.
Making DC usable as AC.
And not just translating, but shaping it, refining the quality. We saw it in action with solar power.
That whole journey from sunlight to usable power.
Peeked under the hood at the H-bridge and PWM.
The clever switching principle.
And understood how semiconductor advances made them so widespread, impacting everything from EVs to our fridges.
It all connects.
They really are more than just converters, kind of the unsung heroes of modern electricity, aren't they?
I think that's fair to say. If you connect it all to the bigger picture, they are absolutely pivotal.
How so?
Well, think about integrating all these different ways we generate power now. Solar, wind, batteries. They often produce DC, or variable AC. Inverters are the key enablers that let us plug all these diverse sources into our existing AC grid and into our homes.
Making everything compatible.
Exactly. They provide that essential adaptability. They ensure that no matter where the electricity comes from, a battery, a panel, the grid, it's delivered in the right form with the right quality for whatever needs to use it. That flexibility is transforming energy.
Driving efficiency, enabling renewables.
Sustainability, reliability, it touches on so much.
That adaptability, that flexibility, it really is the game changer, isn't it? Just pause and think about how many more things become possible simply because we can fluidly change electricity between forms and control its quality so precisely.
Opens up a lot of doors.
What other innovations could this unlock down the road? Smarter grids, more distributed energy. Maybe things we haven't even thought of yet.
The potential is definitely there.
So maybe as you go about your day now, you'll spot where these quiet devices might be working in your car, on a roof, maybe even inside your air conditioner. The invisible labor making our electrified world run.
Hopefully it feels a bit less mysterious now.
We hope so too. Hope you feel more confident about what inverters are all about. Thanks for joining us on this deep dive.
Catch you next time.
We'll catch you on the next deep dive.